and actually all those, all the things that I showed you, these are like articles that published when I was a graduate student. So that was at least 5 or 6 years ago, maybe 4 or 5. But nowadays, for ST-FMR, there's an industry. Well, I typically want to say the ST-FMR industry, and you can see a lot of companies working on this technique. And I will say the technique itself is pretty mature. For instance, I just got an 8-inch wafer full of AMRAM devices from E-Tree, and they all have like pretty high yield. So it's not something that you can't do entire long range. Even for E-Tree, they can provide like high quality AMRAM devices. And this company, Everspin, was a spin-off from Freescale, and Freescale was a spin-off from Motorola. And they started doing MRAM, I think, since early 2000. And they just got their IPO maybe a few weeks ago. And if you check on NASDAQ, then you can see the code name for this stock. It's just MRAM. So it's actually very quite. It's a very exciting news for us, like doing MRAM, because you'll see the thing you've been doing, and it's showing on New York Stock Exchange. It's showing on the board, so and you can buy this share. So it's a very exciting thing. And I heard that Avalanche is a startup company based in California, and they've been also doing a lot of research in MRAM, and I believe that they're also working together with maybe whole companies and other companies and start to provide some products. And also Samsung, of course, has already been releasing their products on the market. And so I believe that for next year, we should see a lot of new things coming out. And there are also a lot of traditional hard drive companies. They also have research centers working on MRAM, for instance, HST, in their ones, and also another startup company, Spin Transfer Technologies, focusing on different types of switching mechanism, and traditional companies like TDK, IBM. They all been working on MRAM and also TSMC, and they got a lot of good people from E-Tree. They also been working on MRAM for a while, maybe 2 or 3 years for this time.
So the ST-FMR is now under production.
At least for Samsung, they've already released. They call it the risk product because use as your own risk, so you can use it. Yes, but not for us. It's mostly for some other applications. Yeah, but not because at the from what I've heard, yeah, from the Korean professor, who told me this news is because they don't want to use MRAM to hit their own DRAM lines, the DRAM market, because DRAM is they're still dominating, so they don't really need to release their MRAM. So I believe like Samsung will have the most stable ST-FMR at least for next year. I'm not sure about TSMC, but they're always pretty secretive. They don't really tell you. But my personal feeling is that Samsung has they have a better chance because they got their they invested in MRAM for a long time, and then they actually bought Brandis, a startup company based in California, maybe 5 or 6 years ago, and they started a lot of joint research program with universities. So part of my PhD funding was from Samsung. So and, in MIT they also got a lot of funding from Samsung. So I believe that they got a lot of good resources. not just research patent, but also students who graduate from these groups. And also, Everspan, they've been doing this for a long time. So I believe that there are a lot of mature companies there that are going to release products. But as for me, I'm going to talk about my own research. Actually, my first project when I landed at Cornell, the first project that my advisor gave me was to do this three-tumor device. And the motivation of doing a three-tumor device was because from the two devices that I just mentioned, one with the with the insulator barrier, which is called a tunnel junction, you have a very high, MR change, like TMR above 100%, so which is good. But in order to do spin torque switching, you have to continuously, applying high voltage, typically like several volts, across your tunnel junction. So that will cause breakdown or backhopping. So the breakdown means that, if you send if the current or if the voltage is too high, you actually damage your barrier permanently. So your TMR will drop, or your device will become open, so or shorted, so you cannot have one TMR anymore. Or because you keep writing all the time, and the sample got heated up, and due to the heating, and the magnetization starts to become unstable. So once you switch it to another direction, and it will switch back. So it causes an error in switching. So that's what we call a backhopping. And that's what we don't want, like in a real device. And spin valve, which is the all-metallic structure, the good thing is it has more reliable switching. So you can apply large voltage, large current, and because they're all metallic, so we don't have to worry that much about breakdown. But the GMR, the MR ratio is only 3%. So the motivation is very simple. So why not we just combine these two together? So we can have such that we can have a high TMR, say 100%, and reliable switching at the same time. And so in order to do that, we started from these two types of standard MTJ and spin valve structures. So for tunnel junctions, like I just mentioned, you typically use MgO as your tunnel barrier, and you use cobalt iron boron, sort of amorphous alloy, magnetic alloys as your ferromagnetic electrodes. And for spin valve, we use cobalt iron boron copper and cobalt iron boron. And the reason why we use cobalt iron boron is because we want this to be compatible with the tunnel junction part. And copper is a typical spacer, metallic spacer layer. So that's the reason why we choose copper. And so we want to combine these two. But how? So in order to do this, I believe that you need to have a very good fab facility. So the first thing is you have to build a large fab facility on campus such that students can do whatever they want to do. And you need to have at least industrial level e-beam lithography tool, because like this device I showed you, it took me 2 years to get this. So this is a spin valve plus MTJ structure before putting down top and middle electrodes. So if you look at this schematic diagram, so we have a tunnel junction at the bottom. So this is the MTJ part, and here we have the spin valve. So imagine that you have a nanopillar about 100 nanometers. It's about 200 nanometers in this case, but imagine that you have a device which is about 100 nanometers in length, and you have to cut, mill through several layers and stop right at the ferromagnetic layer here, using e-beam alignment, lithography, and also some etching techniques, RIE or ionized techniques, and put down these two electrodes almost perfectly on top of this part and this part, and they can't overlap. because right after putting down these two electrodes, we have to put down this aluminum oxide insulator in order to make sure that the current will flow through this part. So the idea is that for the spin valve part, you send current this way through the top electrode to the middle electrode, and you will have spin torque coming from this layer injected into this free layer to do the switching. And once it's switched, then you do the read out using a middle electrode and the bottom electrode. And unfortunately, this was the best device I could get, and I never successfully put down top electrodes without them touching each other. So they always, because this is only maybe the gap is only like 30 or 50 nanometers, and I mean we just use say school level tools. So it's very hard for us to get this type of structure. So this is the best I can get. You can see we have this spin valve part over here, and at the bottom we have this tunnel junction. But then you can see that we have some data, and this is actually from Hitachi Global Storage, and they have this capability of building this kind of device. But even for them, if you look at the switching of this device, they can only switch it from anti-parallel state to parallel state, but you can switch it back. So you can only do like sort of like a one-time switching. That means this device is useless, right? Because if you start from here, then you can switch it to a different state, but you can't switch it back. So it's a useless device. But nevertheless, they just want to demonstrate that you can really pattern this kind of devices, and then you can have sort of separation of current use switching and the readout. So this is from the spin valve part, and this is from tunnel junction part. So theoretically, this is doable, but as a graduate student, this is a very bad project. So that's my first project. But so for the first part, at the end, I talked about my first project is to combine these two very successful, and even if you can have a device, the performance is unsatisfactory. So is there any other possible approach? And of course there is, and that's the reason why I'm standing here as a new faculty member talking about these things, because my project worked. And the reason why it worked is because the spin Hall effect. And I was lucky enough, due to because I stayed there for long enough, so I saw this effect coming out. And one of my previous colleague, Liu started this project at Cornell and started to look into spin Hall effect. And basically, the spin Hall effect is coming from the spin-orbital interaction. So if you consider a normal metal, a transition, for instance, a transition metal like platinum or say tantalum, and if you send current or send electrons through this material, then you will have charge current, of course. But at the same time, due to spin-orbital interaction, electrons with different spins, they'll be repelled or they'll be deflected to different edges. So there will be like a spin accumulation and charge accumulation at the same time, at the edges of the material. And this will give you a spin current, and the spin current will depend on the spin polarization direction of the electron and also the charge current direction. And more importantly, the strength will be characterized by this spin Hall angle. Although nowadays we typically call this spin Hall efficiency or spin Hall ratio, but because this is actually a tangent theta. But nowadays we know this value could be really large, so it's not really that correct to call this angle anymore. But anyway, just consider this as a parameter, and if you take magnitude, the absolute value of this is just the ratio between spin current and charge current. So you can consider this as the conversion efficiency from, say, charge to spin. So the larger the better. Just like for the people who work in solar industry, solar field, we want efficiency higher than, say, how large, 30% or something like that. And we want this to be larger than 100%. Because again, this ratio is just like a definition. So it can be larger than 100%. And actually, in the past, like 2008, there are a lot of theoretical work done, even here in NTU, he did a lot of work on the spin Hall, especially in platinum, from the first principle calculations. And the data I showed here is from more systematic work by Tanaka and co-workers. They showed that the spin Hall angle or the spin Hall conductivity for 4D vacuum materials actually will change sign depending on which side on the periodic table the element is. So for the left-hand side, for instance, tantalum and tungsten, you'll get a negative sign. And for platinum and gold, you'll get positive signs. So that means that if we want to verify what we observe from experimentally is really coming from the spin Hall effect, just check the sign first. And the method that we adopted, actually the method that Liu adopted at that time was a very common technique back at Cornell. We used FMR, a spin torque FMR. But I have to say that nowadays, I think this technique needs a lot of improvement. Although we started this, but later on, you see a lot of different groups using this technique. But Liu himself stopped using this technique. So you know what I mean. Once you do this for a longer time, then you will know that there are a lot of parameters, a lot of things that you have to consider. At that time, in 2011, this is still a very, very new method, and also a very fast method, which allows you to determine the spin Hall effect very quickly. And the device itself is very simple. All you need is a bilayer structure. You just need a normal metal layer, which is the spin Hall material that you want to study, and on top of it is the ferromagnetic material, which is the, for instance, they use permalloy, which is a soft magnetic material that people typically use. And if you send an RF current into this device, then you start to get like FMR, ferromagnetic resonance or oscillation of the magnetization. And if there is a spin Hall effect, and the spin Hall effect will give you a torque, which is the black arrow here, tau ST, which is in the plane. But at the same time, because you have a charge current fully in the normal metal layer, that will give you a Ørsted field. And so the Ørsted field will give you this blue arrow, which is the outer plane torque. And these two torques will give you different symmetries in terms of FMR signal. And so I won't go into details, but this is a very simple FMR measurement setup. We just pick up the DC voltage through this very simple bias T method, and just use maybe a Keith Lee or SR A30, then you can pick up this signal very easily. And anyway, when you see the FMR signal, you'll see it's a combination of a symmetric peak and an anti-symmetric peak. And these two corresponds to the contribution from spin current and charge current respectively. So we will, after getting the data, you decompose the signals into these two terms. And by comparing the ratio of these two, then you can get the spin Hall efficiency, or the spin Hall angle. At least that's what we call it at the time. And that's what we got from cobalt-iron tantalum bilayer system, and also cobalt-iron platinum bilayer system. So you can see the anti-symmetric part are having the same sign. So the blue ones are the same for these two data, which means that Oyster field are the same, which is as we expected. But the symmetric part, which is coming from the spin Hall effect, they have opposite signs. And at least from that time, the spin Hall effect, spin Hall scenario is the only scenario that we think correct and can explain the data we observed. And so for tantalum, it's having this symmetric part and upward, and for platinum, it's pointing downward. So for tantalum and platinum, they should have opposite signs of spin Hall angle. And if you believe that, and you analyze the ratio of these two, and you'll get spin Hall angle of tantalum about minus 15%, and for platinum it's about 7%. So in the past, actually at the beginning, a lot of people who work in the field of spin Hall effect or spintronics, they focus on platinum. But later we found that, so for at least using spin Torque-FMR, it seems that for tantalum, or at least in the high resistivity state of beta tantalum, it has a spin Hall angle with its magnitude almost twice as large as this one. So at that time we think, maybe we should use this to really demonstrate spin torque switching. So now it became like a standard to get your work published, unfortunately, because if you claim that you have a very large spin Hall angle, then people typically will ask you to demonstrate switching. So you can't just use like FMR or some other techniques to say that you have a large spin torque efficiency. You have to really demonstrate switching, but it's actually pretty hard. And so here comes the three-terminal device that I just mentioned. So it's much simpler than the three-terminal device that I mentioned earlier, which is a combination of a tunnel junction and a spin valve. So now you just have a tunnel junction on top of your tantalum layer. So the tantalum is your source of generating spin, and you just send a current through this tantalum channel, and then you will inject spin through the spin Hall effect into this cobalt iron boron layer, and then you can switch the magnetization of this layer through the spin Hall effect. And for the readout, you will measure the magnetoresistance change across this junction. So the sensing current will flow from here to here using a standard lock-in technique with a shunt resistor, and you will measure the change of resistance through the tunnel junction. So these are the data from the device, and using external field induced switching, so by applying external magnetic field, we just want to check the quality of the device. And yes, we have TMR, and about 50%. And more importantly, if we apply current, so this is the current flowing in the tantalum layer to generate spin Hall effect. And we can switch the device from low resistance states, which means that these two layers, they are parallel to each other, and to a high resistance state, which means that the bottom layer has been switched by the current-induced spin Hall effect. And you can see the data is very clean and also very symmetric. And that's also what you should expect from spin Hall effect switching. And of course, at that time, we tried to rule out the possibility of, say, Oyster field, because you have a large current flowing in the tantalum layer, and you should have an Oyster field at the same time. But the symmetry of this switching curve is opposite to what we would expect from Oyster field. So that can be ruled out very easily. And in order to determine the critical switching current density from the switching curve, the switching diagram, and we use the formula that I just showed in the first part of my talk. And we only replaced the spin polarization P with spin-hole angle. So like I said, the spin-hole angle is the efficiency of generating spin, so it's like the value P that I just mentioned. And using this and the data I just showed here, we can estimate from the switching, on the switching measurements, that the spin-hole efficiency of beta tantalum is about 12%. So which is pretty close to the 15% I just mentioned. But this is actually negative 12% because the sign is negative. And you know, since we know that platinum has a spin-hole angle of about 7%, and we also know that for tantalum it's minus 15, so a natural question to ask is whether or not another material with even larger spin-hole angle. So at that time, almost at the same time when we got the result from tantalum, I moved on to tungsten because I know that tungsten is right next to tantalum, and at the same time it's much cheaper than this, and this, and this. So it seems to be a reasonable approach. So just work on tungsten. And for tungsten, actually there are two phases, and it's even more, more complicated than tantalum. Because for tantalum, once you sputter it, typically you will just get the high resistivity state, either amorphous or we call it beta tantalum, whatever, but it's always high resistivity. But for tungsten, it's very interesting. Like if you sputter, say more than 5 or 6 nanometers, or if you cook it like above, say 150 degrees Celsius, that's like right about the typical hot plate temperature, you will get a phase transition from say beta tungsten to alpha tungsten. So basically, you have two phases that you can play with. But of course, that's not the story. At the beginning, I started from the tungsten, and I thought this was one phase, and then later I did some heat treatment, and I found that there's a huge change. So later I realized that there are two phases. And for alpha tungsten, it could be really conductive. So this is, in the thin film form, this is almost close to the conductivity or the resistivity of copper. And typically it's in the BCC phase. And for beta tungsten, it has an A15 cubic structure, and it's typically very resistive, around 150 to 350 micron per centimeter. And for our sputter film, like I just mentioned, like if you sputter a thicker film, you'll get lower resistance. And we can verify that through X-ray diffraction. And more importantly, this spin-hole effect will be phase dependent. So if you work on alpha tungsten or thicker tungsten film, you'll see that there's no symmetric component, which means that the spin-hole effect is small. And if you work on beta tungsten films or thinner tungsten films, you'll start to see a larger symmetric peak, which means that the spin-hole angle is larger. And if you plot the efficiency or the spin-hole angle against thickness, you'll see also this drop. So if you go to thicker films, the alpha phase, the efficiency will drop, which means that the beta tungsten is a much better spin-hole material. And you'll see that the spin-hole efficiency for tungsten or beta tungsten is 30%. So it's even larger than beta tantalum. And even till today, I think beta tungsten is still the largest, the material, the transition metal with largest spin-hole angle in terms of its magnitude. And so since we did the FMR measurement, and so I decided why not just again pattern them into three-terminal devices, and you can see even cleaner switching from this three-terminal device. And from that, we can also estimate the switching efficiency. It's also about 30%. And from those devices, from the switching, I can also estimate the resistivities and also the spin-hole angle. So this phase or resistivity dependence of the spin-hole angle is in good agreement with ST-FMR.